Good afternoon and welcome back. In this session, we explore cycle-consistent generative adversarial networks or cycle GANs and the latest in image-to-image translation. Image-to-image translation means teaching a computer to change an image from one style to another, turning a photo into a painting or making daytime scenes look like night. CycleGAN learns these changes without exact before and after pairs using cycle consistency to map between two domains and back preserving content. Today, we'll discuss how it works, why it's exciting, and where it's used. It's a powerful tool for researchers charting new directions in AI. Today, we'll walk through the agenda and preview what you'll learn. We'll start by recapping GANs and where traditional GANs often fall short. Next, we'll introduce CycleGAN and sketch its architecture at a high level. Then we'll drill into the main components of CycleGAN, showing how the generators and discriminators interact and why cycle consistency matters. We'll highlight the key advantages CycleGAN offers and explain how it differs from classic GANs. After that, we'll look at practical implementations and real-world use cases you might encounter. We'll also discuss challenges, limitations, and possible directions for future work. We'll wrap up with a concise summary and takeaways you can apply. Before we dive deeper, picture GANs as a friendly duel in a studio. A generator starts from noise and a discriminator keeps score, each learning from the other. Through lots of rounds, the painter gets better at fooling the judge, while the judge sharpens its eye for flaws. Up next, we'll see how this back and forth unlocks three practical uses for images. First, image generation, creating realistic pictures and scenes. Second, style transfer repainting content in different artistic looks. Third, data augmentation, generating synthetic examples to train models when real data is scarce. We'll also note the need for checks, bias, quality control, and how researchers measure diversity and realism. Finally, a quick word on responsible use. These tools can speed up design, art, and science, but they require rules, supervision, and careful judgment. Having laid out the basic two-player dynamic, we can turn to the advances that researchers are actively deploying to make GANs more stable, controllable, and available in real-world settings. First, training stability and the quality of gradient signals. A central concern is preserving a well-behaved gradient flow when the generator and discriminator push against each other. To this end, several techniques constrain the discriminator's capacity in a principled way. Spectral normalization, for example, imposes a bound on the spectral norm of each weight matrix, effectively controlling the Lipschitz constant of the discriminator. This tends to prevent exploding gradients and yields more predictable learning dynamics. Another popular approach is the gradient penalty, as in the Wasserstein family of losses, which explicitly encourages the gradient norm with respect to the input to stay close to 1, enforcing a smoother, more meaningful Wasserstein distance between real and generated distributions. Relatedly, the two timescale update rule, or TTUR, suggests using different learning rates for the generator and discriminator, allowing the two networks to adapt at compatible bases and reducing oscillations during training. In practice, these tools are widely adopted to curb mode collapse and to encourage stable convergence, even on higher resolution or more complex datasets. Second, how we measure progress and diagnose failure. The Frischeth inception distance, or FID, has become a standard metric because it compares real and generated data in the feature space of a pre-trained classifier, capturing both fidelity and diversity. Lower FID indicates closer alignment with real data statistics. Complementary metrics like the inception score, precision recall for distributions, and the kernel inception distance offer additional lenses on quality and coverage. It is important to interpret these metrics alongside qualitative assessments and to be mindful of their biases and failure modes, especially when pushing into high fidelity or diverse regimes. Third, architectural and hybrid advancements. Beyond improvements to the laws, researchers pursue architectural innovations. Mini-batch discrimination to encourage diversity within a batch. Unrolled GANs that anticipate the discriminator's responses to stabilize training, and self-attention or transformer-like blocks to capture long-range dependencies. Progressive growing and style-based generators pioneered in StyleGAN and its successors enable finer control over detail and texture. Hybrid models combine GANs with other generative paradigms, such as VAE GANs that marry probabilistic encoding with adversarial refinement, or infogans that promote interpretable latent factors. These hybrids can yield better latent representations, enabling targeted sampling and structured manipulation. Today, we take a closer look at three core image-focused applications of GANs with attention to practical considerations that researchers care about: how we measure success, how we stabilize training, and how we guard against bias and misuse. First, image generation. GANs increasingly produce highly realistic images with controllable attributes and broader stylistic variety. Beyond producing convincing samples, we now emphasize training stability and evaluable quality. Techniques like spectral normalization tighten the Lipschitz constant of the discriminator, reducing training oscillations and encouraging smoother generator learning. Gradient penalties, as in WGAN-GP, impose explicit Lipschitz constraints that improve convergence and sample quality. For control, conditional, and class conditional GANs let us steer attributes or categories and even enable progressive growing or multi-scale architectures to capture fine details at high resolutions. When we evaluate, we move beyond human taste, Fréchet inception distance, and its peers, KID, IS quantify realism and diversity. Perceptual metrics like LPAPS assess visual similarity to real images, and precision recall style analysis help diagnose mode collapse and coverage. Hybrid models combining GAN objectives with diffusion priors or VAE-like encoders offer practical gains in sample fidelity and latent space interpretability. In practice, these advances enable applications from art and visual photography to high-fidelity data synthesis for simulations, always alongside careful bias and safety checks. Second, style transfer. Here, the goal is to alter appearance while preserving content. Unpaired style transfer, epitomized by cycle GAN, benefits from cycle consistency and perceptual losses to retain structure while re-encoding textures and color palettes. Today, researchers push toward multimodal style transfers. A single content image can yield multiple stylistic outputs by injecting stochastic style codes, offering richer creative latitude. Semantic-aware transfers use segmentation maps or learned content representations to maintain important structures, faces, textures, edges during transformation. Evaluation blends perceptual similarity with content fidelity and stylistic alignment. Human studies often complement objective metrics given the subjective nature of style. As with generation, the risk of overbleed or content distortion is real, so robust validation and domain knowledge are essential. Third, data augmentation. Synthetic images can augment scarce real data, balance classes, and improve generalization. Class conditional GANs enable targeted augmentation for underrepresented categories, while domain or style condition generators help bridge dataset shifts. Critical here are quality and diversity checks. Ensure the synthetic distribution matches the real distribution in meaningful ways. FID divided by KID comparisons, downstream task gains, and assess whether augmented data introduces biases or spurious correlations. Hybrid workflows combining augmentation with hard negative mining or uncertainty-guided sampling can maximize gains while containing risk. Always couple quantitative gains with fairness and safety assessments. Otherwise, synthetic data can mislead models or erode trust. In all three threads, the message is clear. Advances in stability, evaluation, and responsible use elevate GANs from curiosity to reliable research partners. Before we dive into the rest, let's keep a few threads running. So far, we've seen how traditional GANs lean on paired data and how that rare alignment can limit where these models can be used. When data comes unpaired or messy, researchers turn to unsupervised or semi-supervised tricks to keep learning from exchangeable pieces. We've also touched on mode collapse, the painter who repeats the same stroke, and why that makes images dull or misleading. Training instability adds another layer of risk, with gradients fading or the competition tipping out of balance. In the next slides, we'll explore practical remedies, how cycle, consistency, and identity mappings help preserve content while translating style, how smarter architectures can stabilize learning, and how balance between generator and discriminator becomes the fulcrum of reliable results. We'll also peek at how these ideas play out in real-world tasks beyond neat, paired datasets. Let's push beyond the clean paired data regime and address a reality check. In the wild, exact pairs are scarce, expensive, or outright unavailable. Paired data can simplify training and boost apparent accuracy, but it creates bottlenecks as soon as you scale, diversify, or transfer across domains. Real-world data is messy, and the requirement for exact correspondences often clashes with the goals of scalability and generalization. This is where the field shifts from supervised perfection to robust learning under unpaired or weakly supervised conditions. What changes when we drop strict pairing? The problem becomes one of learning cross-domain mappings without one-to-one correspondences. Researchers turn to strategies that impose structure without exact pairs. A cornerstone is cycle consistency. Models learn to translate from domain A to domain B and back again, ensuring the original sample is recoverable. This idea underpins cycle GAN and related approaches, enabling tasks like unpaired image to image translation. Multi-domain variants, such as star GAN, extend the idea to several domains with a single model. Beyond translation, you'll see semi-supervised and unsupervised GANs that leverage unlabeled data, self-supervised objectives, and contrastive signals to align representations across modalities. Stability and quality become central concerns with unpaired data, so we lean on architectural and optimization advances. Spectral normalization is now a mainstay for the discriminator. By constraining the spectral norm of weight matrices, it stabilizes training when the data distribution is shifting or less structured. Gradient penalties, notably in WGA-NGP, enforce Lipschitz continuity and produce smoother, more meaningful gradients, reducing mode collapse risk and helping the model learn coherent cross-domain mappings even without paired supervision. Evaluation takes on new importance. Traditional accuracy is insufficient when pairs are absent. We rely on metrics that capture realism and diversity. Frechet inception distance (FID) remains popular for judging the quality and variety of generated samples against real data. Complementary measures like KID, kernel-inspired distance, precision recall analysis for generative models, and task-specific proxy evaluations (e.g.) downstream retrieval or alignment performance provide a fuller picture of what the model actually learns. Hybrid and alternative frameworks further widen the toolbox. VAE GAN hybrids combine likelihood-based and adversarial objectives for better latent structure. Diffusion models offer another path for high-fidelity generation with different training dynamics. Contrastive and self-supervised losses can help align cross-model representations when explicit pairs are scarce. In practice, the choice between paired, semi-supervised, and unpaired strategies hinges on data availability, desired generalization, and the tolerance for annotation cost. Mode collapse remains a practical hurdle even when we use cycle-consistent architectures like CycleGAN. In advanced workflows, we see the generator latch onto a small set of translations or appearances and then reproduce them relentlessly, undercutting the very diversity we rely on to model complex cross-domain relationships. What underpins this in training are the gradients we feed the networks. If the discriminator consistently rewards a narrow set of outputs, the generator can game the signal and the feedback loop narrows rather than broadens the learned distribution. To counter this, we can fortify the critic and the signaling path in several ways. First, stabilize the discriminator with spectral normalization. By constraining the spectral norm of each layer, we enforce a controlled Lipschitz constant, yielding smoother, more informative gradients for the generator. Parallelly, gradient penalties such as the WGA-NGP penalty explicitly push the gradient norm toward 1 on interpolations between real and fake samples, reducing abrupt shifts that encourage mode sticking. Together, these reduce the tendency to collapse onto a few modes. Second, refine the training dynamics. The 2 timescale update rule, carefully chosen learning rates for G and D, helps maintain a healthier contest between the networks. Techniques like unrolled optimization provide the generator with a longer horizon of discriminator behavior, mitigating overfitting to transient discriminator weaknesses and promoting broader exploration. Third, inject diversity-promoting clauses. Mini-batch discrimination tools allow the discriminator to compare multiple samples jointly, discouraging sameness. Mode-seeking losses explicitly reward diverse outputs for a given input. Perceptual or content-preserving losses, for example, a VGG-based perceptual loss can be combined with cycle consistency to maintain semantics while relaxing low-level sameness, helping the model explore a broader space of plausible translations. Fourth, consider hybrid models and architectural choices. Hybrid GAN approaches that pair a VAE or a diffusion prior with cycle objectives can improve coverage of the data manifold. Multi-scale discriminators, residual connections, and richer architectural priors help the networks represent more varied transformations and detect subtle high-frequency differences that signal underrepresented modes. Evaluation matters. Use freshet inception distance to quantify how close the generated set is to real data in distribution, alongside inception score, precision divided by recall for generative models, and perceptual similarity metrics like LPAPS to gauge diversity without sacrificing quality. In short, combining stronger regularization, smarter training dynamics, diversity-focused losses, and thoughtful hybrid designs gives us a path to less brittle generators. Think of a painter who learns to vary strokes and palettes rather than repeating a single motif. With these tools, our models begin to capture a richer spectrum of the data. Let me take the next step and translate the instability you see in practice into concrete stabilizing levers researchers actually use. The core problem remains the two-player game, but the remedies now target specific failure modes we consistently observe during training: vanishing gradients, mode collapse, and oscillatory dynamics that prevent steady progress. First, objective reshaping and constrained enforcement. The standard minimax laws can yield fickle gradients when the discriminator becomes too confident. A widely adopted remedy is to switch to a Wasserstein-based objective with a gradient penalty, WGAN-GP. This formulation replaces the original divergence with the Earth-Moore distance, which provides smoother, more informative gradients even when the discriminator isn't perfect. The gradient penalty enforces a soft Lipschitz constraint, mitigating sharp discriminator responses and helping the generator receive meaningful updates. 2. Complementary constraint techniques often go hand in hand: spectral normalization and gradient penalties. Spectral normalization explicitly constrains the spectral norm of each layer in the discriminator, ensuring one Lipschitz behavior in a more lightweight way than a full penalty. It stabilizes gradient flow across training steps and reduces the tendency for the discriminator to overfit on a small set of features. In tandem, gradient penalties, R1 divided by R2 on real or fake data, or the WGAN-GP penalty on interpolations, keep the optimization landscape well behaved, making the training dynamics more predictable. Diagnostics and evaluation matter as early warning systems. In addition to qualitative inspection, we rely on metrics that track both realism and diversity. Freshet inception distance is the workhorse. Lower values suggest that generated images occupy a similar distribution to real images in feature space. Kernel inception distance and calibrated precision recall metrics provide complementary views on mode coverage and sample quality. Monitoring these metrics over time alongside gradient norms and the relative losses of G and D gives a clearer picture of whether instability is improving or simply masking quality fluctuations. Hybrid and architectural strategies also play a crucial role. Conditional GANs inject structured information to stabilize learning and improve controllability. Progressive growing and self-attention mechanisms help the model learn both core structure and long-range dependencies, addressing global coherence that often underpins perceived instability. Regularization schemes and architectural tweaks such as feature matching losses, unrolled GANs, or mini-batch discriminators promote diversity and discourage collapse without sacrificing fidelity. Finally, practical training choreography matters. The two timescale update rule uses different learning rates for the generator and discriminator to balance their learning paces. Regularization, normalization, and careful scheduling of batch sizes and data augmentations further reduce oscillations. As we move forward, we'll unpack how CycleGAN makes unpaired image translation work. The core idea is to learn two mappings, A to B and B to A, trained in parallel within a GAN setup where the generators and discriminators push each other toward realism. The crucial twist is cycle consistency. If we translate from A to B and back again, we should recover the original A, keeping content intact while altering style. With two generators and two discriminators, each direction is guided toward convincing the other domain, and a cycle loss softly ties the directions together without demanding exact matches. We'll see practical examples changing day to night, turning sketches into photos, or converting paintings to real scenes while preserving shapes and structure. Finally, we'll note the broader impact. Flexible, data-efficient style transfer for art, science, and even medicine with proper attribution. CycleGAN gives us a practical path for unpaired image-to-image translation by learning two mappings, A to B and B to A, with cycle consistency tying the directions together. But in a research setting, several advanced ideas extend this foundation to yield more reliable, high-quality translations and to broaden where cycle GAN can be applied. Let me outline how we think about these enhancements and how to reason about them when you design experiments. First, training stability and regularization. Discriminators in GANs can be unstable. A common remedy is spectral normalization on the discriminator weights, which constrains the Lipschitz constant and improves generalization of the judge. Another powerful approach is a gradient penalty, as in WGAN GP, which enforces smooth, well-behaved gradients with respect to inputs. Together, these techniques reduce training oscillations and help the two generators learn meaningful, stable mappings in the unpaired setting. Second, loss design beyond the vanilla cycle loss. In practice, you typically balance adversarial losses for realism with cycle losses for content integrity. An identity loss where you pass images already in domain A through G, A to B, and expect near identical outputs when the input already belongs to the target domain helps preserve color and low-level structure. The weights of these terms lambda, cycle for the cycle loss, and lambda, identity for the identity loss are crucial. They often require empirical tuning on the target domain to avoid over-regularizing style transfer at the expense of content. Third, architectural and perceptual enhancements. Many implementations deploy dual generators and discriminators with architectural choices such as residual blocks, skip connections, and instance normalization to improve style transfer while preserving content. Multiscale discriminators capture both global and local statistics, which is important for textures and fine details. Incorporating perceptual or feature-based losses using a pre-trained network e.g. VGG or a modern vision backbone can encourage the translated image to align with high-level semantic features while maintaining lower-level fidelity. Attention mechanisms can focus the style transfer on semantically relevant regions, reducing global artifacts. Fourth, evaluation and metrics. Beyond qualitative assessment, researchers now rely on Frege inception distance to quantify realism and similarity to the target domain along with KID. Perceptual metrics like LPPS can measure content preservation, and human studies remain valuable for evaluating perceived quality. Ablation studies and controlled swaps of loss terms help isolate the contribution of each component. Fifth, extensions and hybrid models. You can blend cycle GAN with temporal or video consistency constraints for unpaired video translation, or add segmentation-guided losses to respect object boundaries. Hybrid models that combine GAN losses with traditional style transfer objectives or domain-adaptive components enable broader applicability, including medical imaging or satellite data where both fidelity and interpretability matter. In short, cycle GAN remains a flexible scaffold. By tightening regularization, enriching losses with perceptual and identity terms, refining architecture, and adopting robust evaluation, we can push unpaired translation toward both higher fidelity and wider applicability. Building on the core idea of cycle consistency, this slide highlights how the practical power of cycle GAN emerges when we push beyond the basics with stabilization and principled evaluation. In modern implementations, the dual generator divided by dual discriminator setup is complemented by refinements that make unsupervised translation both more reliable and more interpretable for researchers. A central line of improvement concerns the training dynamics. Spectral normalization is often applied to the discriminators to enforce a Lipschitz constraint, effectively tempering the Jacobian and preventing explosive gradients. This reduces training oscillations, particularly for high-resolution images, and helps the discriminators provide more stable, meaningful feedback to the generators. Alongside that, gradient penalties a la WGAN GP penalize deviations of the gradient norm from one-along interpolations between real and fake samples. This leads to smoother optimization, mitigates mode collapse, and yields more coherent translations across both directions, AB. In practice, the loss landscape becomes a weighted blend. Adversarial losses for both directions, the cycle consistency loss that enforces ABA and BAB reconstructions, and often an identity loss that discourages unnecessary color or style shifts when inputs already resemble the target domain. Many researchers also incorporate gradient penalties or spectral terms into the overall objective to reinforce stability across training runs. The balance of these terms through the loss weights often dictates how faithfully content is preserved versus how aggressively style is transferred. Evaluation shifts from qualitative inspection to robust metrics. The freshet inception distance FID remains a staple for gauging realism and distributional similarity between generated and real images, while kernel inception distance provides a non-parametric alternative with favorable statistical properties in some regimes. Perceptual similarity metrics such as LPAPS quantify how humans perceive differences, offering insight into whether the content remains semantically aligned after translation. When reporting results, it is prudent to present a small suite of metrics to capture realism, diversity, and content fidelity, and to discuss any observed trade-offs. Hybrid and auxiliary techniques further sharpen performance. Attention mechanisms can guide the model to preserve structural details while altering style, and auxiliary semantic or segmentation losses can enforce content-consistent regions across domains. Some works explore joint training with diffusion-inspired refinements or multi-scale discriminators to capture both global structure and fine textures. In practice, you'll want to monitor cycle consistency alongside perceptual and distributional metrics, tune loss weights carefully, and document the credit for foundational ideas and data sources. And as you prototype, remember the guiding analogy. Two rooms connected by a mirror success means translations that faithfully return you to the original arrangement, not merely convincing snapshots of the other side. Next, we drill into cycle GAN style translations by wiring two generators into a single loop. G converts X to Y while trying to keep the scene intact, and F does the reverse. The two-way setup means we can learn style transfer without paired images. We'll then bring in a pair of discriminators, dx and dy, each judging realism in its own domain and guiding the corresponding generator. The detectors push the translators to respect X features and Y texture. After that, we examine cycle consistency. Forward cycle checks from X to Y back to X, and backward cycle checks from Y to X back to Y. These checks ensure content stays stable even as appearance changes. The result is more natural translations with unpaired data covering tasks from daylight to night, weather, or artistic styles. We'll close with how this framework keeps training robust and generalizes better. Today, we expand cycle GAN style dual generators into a more nuanced, research-ready perspective. In this framework, two generators operate in tandem. G translates X, Y, and F translates Y, X. The core idea remains: G learns to shift style while preserving content, and F provides a reciprocal check that helps undo mistakes and keep structure intact. The cycle consistency constraint is the backbone. If you map X to Y with G and then return to X with F, you should arrive near your original image. This bidirectional pressure prevents arbitrary edits and supports meaningful, content-preserving translations even without paired samples. Beyond the basic losses, several advanced components sharpen performance and stability. First, adversarial losses on both directions G against a discriminator D, Y, and F against D, X drive realism in each domain. To stabilize training, many implementations employ spectral normalization on discriminators, which constrains the Lipschitz constant and mitigates exploding gradients. Gradient penalties, as in WGAN-GP, offer an alternative or complementary route by enforcing smoothness in the critics landscape, further stabilizing updates when learning complex cross-domain mappings. You'll also often see an identity loss term. When an input already lies in the target domain, the network should leave it largely unchanged. This discourages color shifts or stylistic changes when none are needed and helps preserve content, particularly for texture and lighting cues. Patch-based discriminators, patch GAN, are popular because they focus on high-frequency details and local realism, which is especially important for fine-grained textures and regional style transfers. Evaluation is crucial in unpaired translation. Frechet inception distance and its cousin KD provide quantitative gauges of how close the generated distributions are to real samples, while perceptual metrics like LPAPS assess human-aligned differences in style and content. Human studies remain valuable, but these metrics give you repeatable baselines for comparing model variants. Keep in mind that FID divided by KID are sensitive to dataset characteristics, so you should report complementary statistics and error bars across multiple runs. Hybrid approaches illuminate further possibilities. For instance, integrating variational autoencoder components can enforce latent structure consistency, or coupling cycle GANs with diffusion-based refiners can yield sharper final outputs. Multi-scale discriminators and loss terms can capture both global layout and local detail, enhancing stability and realism. When you combine these elements thoughtfully, spectral normalization, gradient penalties, identity and cycle losses, robust evaluation, and selective hybrids, you obtain translations that are not only convincing but also robust to domain shifts and diverse inputs. Imagine the dual discriminator setup not just as two separate judges, but as a two-sided validation framework that quietly but powerfully guides the generator in both directions of the translation. First, beyond the intuitive roles of D, X, and D, Y, there are concrete techniques that stabilize and sharpen their guidance. Spectral normalization, applied to both discriminators, is a common starting point. By constraining the spectral norm of each weight matrix, we cap the Lipschitz constant of the critics, preventing them from becoming overly explosive. This yields smoother, more informative gradients for the generator and reduces oscillations during training. In tandem, gradient penalties such as the WGAN GP style penalty enforce a principled one Lipschitz condition by penalizing the norm of the discriminator's gradient with respect to its inputs. When you apply a gradient penalty to both D, X and D, Y, you stabilize the learning signal in both domains and help the two discriminators stay compatible as the generator evolves. On the evaluation front, you go beyond qualitative checks. Freshet inception distance, or FID, is a workhorse for measuring realism and distributional similarity of generated samples to real samples in the target domain. You typically compute FID for X to Y translations and the reverse to quantify how convincingly the model captures the Y domain statistics. Kernel inception distance KID offers a memory-efficient alternative, while LPIPS provides perceptual similarity to ground truth images, helping you gauge whether structural and textural details are preserved. In domain-specific settings, you may also track SSIM or other perceptual metrics to ensure content fidelity. Importantly, high performance on both D, X and D, Y should correlate with favorable FID divided by K divided by LPIPS scores, signaling that the dual feedback is steering the translation toward real, domain-consistent appearances. Hybrid modeling and regularization strategies add another layer of robustness. A GAN VAE hybrid, for instance, can preserve content via an encoder while using the dual discriminators to enforce realism in X and Y domains. Auxiliary classifiers or domain condition heads can be attached to D, X, and D, Y to inject semantic or style constraints, further guiding the generator. Some researchers couple these discriminators with cycle-like or content-preserving losses to maintain X features while adopting Y style, but with a careful balance so the discriminators do not fight the content constraints. Practically, you monitor both discriminators' losses, tune the loss weights to keep D, X, and Dy in sync, and employ a balanced update schedule, often TTUR-like strategies, to prevent one discriminator from overpowering the other. The goal remains clear. Dual discriminators provide a robust, two-sided gate that pushes the generator toward translations that are not only visually authentic in both domains, but also faithful to the essential X and Y domain features. Cycle consistency is a practical constraint that keeps learned image translations honest about what the content actually is, not just what it looks like after a style switch. In many translation tasks, a model could produce visually striking outputs by reimagining the scene, but at the cost of losing the underlying structure. Cycle consistency tackles this by enforcing a reversible path. You translate from one domain to another and then back again, and the result should resemble the original. This is not just a pretty constraint. It acts as a stabilizing principle for learning a reliable mapping between domains. Let me unpack forward cycle consistency first. Imagine you start with an image in domain A and transform it to domain B. Think of turning a photograph into a painting. Now translate that painting back to domain A. If the system is well behaved, the round-tripped image should reproduce the original scene. Same objects, same layout, same spatial relationships, and key details. The goal is to preserve content while allowing the style to change. If the reconstruction deviates, the forward cycle provides a clear signal that something about the AB mapping is distorting essential information. In practice, this discourages the model from making arbitrary or content-destructive changes in pursuit of stylistic gains. Backward cycle consistency follows the same logic in the opposite direction. Start with an image in domain Y, translate back to domain X, and then translate again to Y. The final image should be very close to the starting one. This enforces bidirectionality. The transformation XY should be mutually compatible so that switching styles and returning preserves the core content. It's a reversible shortcut that helps ensure the translation preserves not just superficial colors or textures, but the meaningful content and structure of the scene. Why is this important? Without cycle checks, a translator could produce outputs that look novel or appealing at first glance but misrepresent the original scene, adding, removing, or reordering elements in ways that are unacceptable for many applications. Cycle consistency makes those errors visible and learnable, guiding the model to respect layout and objects while still permitting useful style changes. The math can be intricate, but the underlying idea is simple: keep content stable across translations. In practice, researchers implement two checks: the forward cycle check ABA and the backward cycle check YXY. Together, they shape reliable bidirectional mappings that preserve content integrity while enabling desirable stylistic variation. This is the essence of cycle consistency in image translation, a practical safeguard that supports reliable performance across tasks from denoising to style transfer. Next, we'll unpack how CycleGAN builds a generator that translates between styles while keeping the core scene intact. First, the generator architecture uses ResNet blocks with skip connections that let information flow around layers, helping preserve shapes and textures as style changes. We'll then see how the encoder-decoder pair downscales an image to capture essential features and then recreates it at the original size, blending content with the new style. After that, we examine PatchGAN, the discriminator that judges many tiny patches rather than a single verdict, boosting texture, realism, and training efficiency. Finally, we connect the three learning signals: adversarial loss, cycle consistency loss, and identity loss, and explain how their balance guides translation from one domain to the other, keeping results convincing without losing identity. We'll keep the intuition concrete with quick comparisons. In this section, we'll go beyond the core builder blocks and discuss how modern enhancements tune the CycleGAN generator for sharper, more faithful cross-domain translation while keeping training stable and efficient. We start with the architectural backbone and why it matters. The generator relies on ResNet style blocks to preserve content while easing the learning of style deltas. Each residual block provides a shortcut path that keeps information flowing and supports deeper networks without vanishing gradients. In practice, you'll see downsampling in the encoder to capture salient features and upsampling in the decoder to reconstruct the image at the target resolution. This encoder-decoder pairing, augmented by skip-like paths through the residual blocks, helps the model separate content shapes, layout, from style, color, texture, which is crucial for meaningful style transfer without paired data. Moving to stabilization and regularization, several refinements are now common. Spectral normalization, originally popular on discriminators to enforce Lipschitz constraints, can also be applied to generators to temper extreme updates and improve convergence, especially in deep or multi-scale setups. Gradient penalties, as in WGAN GP, can be incorporated to enforce smoother gradients and reduce mode collapse, yielding more reliable training when translating challenging textures or large domain gaps. These penalties work in concert with the cycle consistency and identity losses, which together constrain mappings to be invertible and content preserving. Normalization and normalization-aware design deserve attention. Instance normalization is standard in style transfer networks, but researchers increasingly experiment with adaptive or conditional normalization, for example, Adain-like mechanisms, to inject style statistics more explicitly into the generator. Attention mechanisms, self-attention blocks, or non-local blocks are another powerful addition, enabling the generator to model long-range dependencies and align global structure with localized textures, which is especially helpful when cross-domain changes involve global layout or scene context. Hybrid architectural choices further refine performance. Some variants combine the ResNet backbone with unit-style skip connections to preserve fine-grained details. Multi-scale or patch-based approaches, both in the generator and in discriminators, encourage fidelity across texture scales, producing crisper textures and fewer artifacts at edges. Finally, evaluation is essential. Beyond qualitative inspection, use metrics such as freshet inception distance and kernel inception distance (KID) to quantify realism, and perceptual similarity measures like LPPS to gauge how faithfully content and style are preserved perceptually. Careful ablations and multiple metrics help ensure that architectural gains translate into robust, publishable improvements across datasets. In short, the generator design in cycle GAN benefits from deeper residual pathways, stabilized training via normalization and penalties, attention and normalization strategies to control style transfer, and hybrid multi-scale configurations capped with rigorous evaluation. These elements collectively yield sharper, more coherent translations with stable training dynamics. Thank you. Building on PatchGAN's local focus, there are several ways we can push its capabilities beyond the basic description to improve stability, fidelity, and evaluability in real-world research settings. First, consider regularization and Lipschitz control. PatchGAN inherently evaluates many small regions, so stabilizing those region-wise gradients is crucial. Spectral normalization applied to each convolutional layer in the discriminator constrains the spectral norm of the weight matrices, effectively bounding the Lipschitz constant per layer. This helps prevent exploding gradients and makes training more predictable when you stack patch GANs in multiscale or hybrid architectures. In parallel, gradient penalties such as those from WGA and GP can be employed on interpolations between real and fake patches. A patch level penalty term, penalizing deviations of the gradient norm from 1, encourages a smoother, more stable discriminator surface and reduces mode dropping that can arise in patch-based training. Second, think about loss formulations and how the patch GAN outputs are aggregated. Patch GAN typically yields a matrix of real divided by fake predictions, one per patch, which are then averaged or pooled to form the final discriminator signal. While binary cross entropy is common, many groups have found that hinge losses or least squares objectives can yield sharper, more stable textures in the generated outputs. When patch GAN is used in conditional tasks such as image translation, you can combine the patch level adversarial loss with a perceptual or feature reconstruction loss L1 divided by L2 to preserve both global structure and local texture. Third, evaluation and interpretation. Global metrics like FID provide an overall sense of distributional similarity but can mask local texture fidelity. Patch-focused textures often correlate with higher perceptual realism even when FID is modest. To address this, combine global metrics FID-IS with local measures such as LPI-PS on texture-rich regions or patch-wise FID computed over sampled patches to quantify regional realism. For high-resolution tasks, multi-scale evaluation is informative. Assess at several patch sizes and compute scale-specific FID divided by LPI-PS to diagnose where textures succeed or fail. Fourth, hybrid and multi-scale designs. Patch GAN excels when used alongside a global discriminator or within a multi-scale discriminator stack. A global path enforces coherence across distant regions, while patch GAN guards fine detail. You can also implement a hierarchy of discriminators operating at different patch sizes A, G, 42x, 42, 70x, 7142x, 142 to capture textures at multiple granularities. Attention mechanisms within patches or cross-patch attention can help propagate long-range texture consistency without sacrificing locality. In practice, these hybrids often deliver both sharp local textures and plausible global structure. Lastly, practical guidance. Choose patch size with resolution and texture scale in mind. Larger patches capture broader textures but increase computational load. Use spectral normalization and, if feasible, a gradient penalized objective to stabilize training. When reporting results, accompany global metrics with patch-level texture analysis to convey the texture realism patch GAN brings to texture-rich synthesis tasks. Let me build on the three losses you've already seen by outlining how researchers push cycle GAN beyond its basic recipe. The goal is not only realism, but stability, fidelity, and transferability across diverse domains. First, stabilization tricks for the discriminators. Spectral normalization constrains the Lipschitz constant of D, which helps prevent overly confident gradients that destabilize generator updates. In practice, you insert spectral normalization into the D architecture, yielding steadier adversarial signals as you push translations across challenging textures or high-frequency details. This becomes especially valuable when cycle and identity terms push the model toward fine-grained fidelity rather than coarse realism. Second, gradient penalties and alternative losses. Gradient penalty terms, exemplified by WGAN GP, encourage smooth discriminator behavior along interpolations between real and fake samples. In cycle GAN setups, This tends to reduce artifacts and mode dropping that pure adversarial losses can provoke, particularly when the cycle constraint is underspecified for complex scenes. Many researchers also experiment with hinge loss on the discriminator, which often yields crisper boundaries and more stable optimization than the classic binary cross entropy. Third, where the objective is measured and guided. Evaluation has progressed beyond qualitative inspection. Frequent inception distance is now a standard metric to quantify realism and diversity between generated and real target domain images. Perceptual similarity metrics such as LPIPS complement FID by focusing on perceptual content fidelity. Kernel-based distances like KID offer an alternative that can be more robust in some regimes. Researchers pair these with structural metrics like SSIM or even task-driven evaluations to ensure translations preserve layout or semantics in addition to appearance. Fourth, hybrid models that extend the cycle GAN paradigm. You can augment cycle and identity objectives with perceptual losses that compare features from pre-trained networks, for example VGG features, to better preserve content during stylization. Self-attention modules, as in attention-augmented cycle GAN, capture long-range dependencies and improve consistency in complex scenes. There are multi-domain extensions, A, G, star GAN variants, that share encoders across domains, blending cycle-like constraints with domain conditioning. Variational components, VAE GAN hybrids, also appear, combining probabilistic latent structure with adversarial realism to improve diversity and controllability. Practical takeaway: balance remains central. Start from established weights for adversarial, cycle, and identity terms, but be prepared to tune them in light of stability metrics, spectral norm behavior, gradient penalties, and the chosen evaluation suite FID, LPIPS, SSIM. And always couple quantitative metrics with qualitative checks across representative scenes. In short, advancements in normalization, penalties, robust evaluation, and hybrid architectures collectively enhance CycleGAN's ability to produce visually compelling, content-faithful translations without sacrificing identity. Before we close this section, let's connect the dots from what CycleGAN does to why it matters in practice. The heart of the approach is simple to describe but powerful in effect: two translators, two critics, and a cycle constraint that keeps the meaning of the scene intact as styles swap back and forth. Because the model learns from many examples per domain, it preserves structure while allowing colors, textures, and style to change. In the next slides, we'll see how that balance translates into real results, from turning daytime photos into night scenes or paintings to translating medical scans for consistent interpretation, all without exact image pairs. We'll also touch on domain adaptation, getting a model to work when the source and target data come from different devices or lighting conditions, and what keeps training stable when the data grows. Finally, we'll summarize practical takeaways for building flexible, data-efficient translation systems. Building on the bidirectional cycle-consistent framework we discussed, there are several refinements that make CycleGANs more robust and applicable to real-world research settings. These advances address stability, fidelity, and the practical challenge of evaluating unpaired translations in a rigorous way. First, consider stabilization and regularization. Spectral normalization is a popular technique applied to discriminators to constrain their Lipschitz capacity, reducing training oscillations and helping the model learn more reliable boundaries between real and translated images. Relatedly, gradient penalties, as in WGANGP, penalize deviations from smooth, Wasserstein-like gradients, promoting steadier convergence when the domains differ substantially. In practice, many implementations adopt a hinge or relativistic GAN loss, which can yield crisper textures without sacrificing the global coherence of the translation. Second, architectural and perceptual refinements. Patch GAN discriminators continue to be effective for capturing high-frequency details by focusing on local image patches, which complements the global cues learned by the generators. A multi-scale discriminator setup, where you evaluate realism at several spatial resolutions, helps the model judge both global structure and fine textures. Beyond adversarial losses, identity loss can be incorporated to encourage preservation of color and style when the input already belongs to the target domain, and perceptual or feature losses based on a pre-trained network can help maintain semantic content and stylistic consistency across translations. Third, evaluation and metrics. With unpaired data, traditional pixel-wise accuracy isn't meaningful, so practitioners increasingly rely on Frechet inception distance phi or kernel inception distance key to quantify realism and distributional similarity alongside LPIPS for perceptual similarity. Human studies remain valuable for assessing believable style transfer and content preservation. It's crucial to report multiple metrics and to consider domain-specific baselines, since a single score can be misleading in unpaired setups. Fourth, hybrid and extension ideas. Hybrid models that combine cycle GANs with attention mechanisms or semantic segmentation cues can improve content alignment, especially in complex scenes. There is growing interest in integrating cycle GAN concepts with diffusion models or variational ideas to handle multimodal translations, where a single input could map to several plausible outputs by introducing controllable latent factors or style codes. Such extensions move cycle GAN from a one-to-one translate and back paradigm toward richer, more flexible domain adaptation. Finally, practical guidance. Start with a stable backbone, apply spectral normalization and a modest gradient penalty, and experiment with multi-scale discriminators. Balance the cycle and identity losses with thoughtful weights and monitor both FID divided by KID and perceptual consistency across progressions. With these refinements, cycle GANs become not just a curiosity for unpaid data, but a dependable tool for cross-domain research. Cycle GAN gave us a practical way to translate images without paired data by enforcing cycle consistency and preserving the overall structure. Building on that foundation, there is a family of stability and fidelity enhancing techniques that researchers routinely incorporate to push translation quality toward realism and reliability. First, consider stability and regularization. Spectral normalization applied to the discriminators and sometimes to generators constrains the Lipschitz constant of networks, preventing runaway weight scaling and stabilizing training dynamics. This tends to yield steadier gradients and more consistent learning signals across epochs, which helps the two translators converge to complementary mappings. Another common line of work brings gradient penalties, such as the WGAN GP approach, into the cycle GAN objective. The gradient penalty enforces smooth, contractive behavior of the discriminator with respect to its inputs, reducing artifacts and sharpening the boundary between real and translated images. Together, these tools address a core challenge in unpaid translation, balancing realism with the risk of destabilized optimization. Second, architectural and objective enhancements directly impact translation fidelity. Patch-based discriminators, which judge realism at the level of local image patches, encourage high-frequency detail and texture consistency across the translated image, aligning well with the cycle consistency constraint. Identity loss can be added to encourage the network to leave images already in the target domain largely unchanged, which helps preserve color palettes and global appearance when they should be preserved. Perceptual losses, computed from pre-trained networks, can further encourage the translated image to maintain high-level semantic features that align with the source domain, reducing perceptual drift even when pixel-level differences are large. Third, robust evaluation and diagnostic tools are essential. Frechet, inception distance, and related metrics like KID provide a quantitative measure of how close the translated image distribution is to real samples in the target domain, capturing both quality and diversity. Perceptual similarity measures A, G, and structural metrics like SSIM or PSNR can offer complementary insights into whether semantic content is preserved. Human studies remain valuable for assessing realism and task-specific acceptability, especially in sensitive domains. Fourth, hybrid and extended models broaden cycle GAN's applicability. Multi-domain frameworks A, G, StarGAN style reuse a single translator with domain conditioning to handle several target styles, while attention and segmentation guided variants encourage translations to respect structure in regions of interest, reducing unintended edits. In medical imaging, these approaches can highlight clinically relevant features while maintaining anatomical fidelity, though they demand thorough validation to avert misleading artifacts. Thank you. Building on the core cycle consistency idea, there are several advanced directions that researchers increasingly exploit to push cycle GAN from a reliable baseline toward robust, publication-worthy tools. First, stability and convergence have a grown importance. Spectral normalization, originally proposed to stabilize discriminators, helps bound the discriminator's Lipschitz constant and reduces training oscillations. In practice, applying spectral norm to the discriminator and sometimes the generator yields steadier gradients and more consistent convergence across diverse domain pairs. Gradient penalties, most famously the WGAN GP formulation, offer another path. Instead of relying on specific loss forms alone, we add a penalty on the gradient norm with respect to inputs to enforce a softer Lipschitz constraint. When combined with cycle and adversarial losses, these penalties reduce mode-driven oscillations and promote smoother, more diverse mappings. You may also see the TTUR concept using different learning rates for the generator and discriminator to balance progress and prevent the detector from overpowering the generator early in training. Second, loss design and evaluation become more nuanced as models scale. The cycle consistency term remains central, but practitioners routinely layer in auxiliary objectives. Identity loss, for example, helps preserve color and perceptual attributes when translating within the same domain. Perceptual or style consistency losses computed from pre-trained features encourage outputs to maintain high-level structure while adopting target domain textures. On the evaluation side, beyond qualitative inspection, researchers employ freshet inception distance and its counterpart KAD to quantify how close the generated distribution is to the target domain's distribution in feature space. Perceptual similarity metrics like LPI-PS and content preservation measures such as SSIM divided by PSNR in certain settings provide additional levers for judging realism and fidelity. Importantly, cycle consistency error can be tracked as a diagnostic. If a forward-backward mapping fails to recover the original image, that signals misalignment in content capture. Third, there is increasing interest in hybrid models that blend cycle GAN with other paradigms. Attention mechanisms, self-attention or transformer-inspired blocks allow the model to focus on salient regions during translation, improving structural preservation in complex scenes. Hybridizing with variational components or latent variable encoders enables disentanglement of content and style, offering finer control over the translation and better generalization across subtle domain shifts. Finally, while cycle GAN is inherently two-domain, extensions to multi-domain scenarios via domain-guided encoders or shared latent spaces, and comparisons to domain-agnostic approaches like star-GAN style architectures provide practical guidance for deployment in heterogeneous settings. In short, cycle GAN's core principle cycle consistency retains its value, but the frontier now includes stability techniques, richer objective sets, rigorous, multifaceted evaluation, and hybrid architectures. These enhancements deepen reliability, generalization, and interpretability across real-world applications. Cycle GAN reframes cross-domain translation as a bidirectional, unpaired learning problem. But there are advanced angles worth highlighting for researchers aiming to push the method beyond baseline performance. First, stability. While cycle GAN already uses two generators and two discriminators, stabilizing training benefits from regularizing the discriminators. Spectral normalization, applied to the discriminator weights, constrains their Lipschitz constant and reduces training instabilities that arise when the two domains differ in texture or content. In parallel, gradient penalty ideas from WGAN GP can be integrated to enforce smoothness of the discriminator's response with respect to its inputs, further mitigating sharp gradient excursions that derail cycle learning. Second, refinement of the loss landscape. The three-term objective adversarial, cycle consistency, and identity losses works well, but balancing them is non-trivial. The cycle loss enforces reversibility, ABA is approximately equal to A, while the identity loss encourages content preservation when the input already lies in the target domain. Researchers often tune the weights to prevent over-regularization, which can erode stylistic changes. Perceptual or feature-based losses derived from pre-trained networks can be layered on top of the traditional L1 divided by L2 cycle terms to encourage high-level content consistency, particularly for maintaining structure in medical or scientific imagery. Third, architectural and evaluative enhancements. The discriminators in cycle GAN are frequently patch GANs, which focus on local textures and can deliver more convincing microdetails. Multiscale discriminators extend this idea to capture both fine and coarse structure, improving overall realism. On the generator side, attention mechanisms or architectural variants that separate content from style can help when cycles must preserve spatial semantics in complex scenes. Hybrid models also emerge, combining cycle GAN with perceptual losses or with multi-domain frameworks, for example, star GAN style conditioning, to support more than two domains without retraining separate pairs. Evaluation is another frontier. Beyond qualitative assessment, quantitative metrics like the Frequent Inception Distance (FID) provide a global realism score for the translated images, while LPIPS gauges perceptual similarity to reference images. For content preservation, cycle consistency error remains informative, but augmenting it with human studies or task-based metrics (AG) downstream segmentation or classification stability on translated images offers richer insight. Finally, limitations and extensions. When domains are highly dissimilar or lack variation, the model may default to artifacts or rely on shallow style transfers. Extensions such as unit, discogan, or multi-domain variants e.g. illustrate how shared latent spaces or conditional controls can broaden the applicability. In short, CycleGAN's core idea, bidirectional mapping with cycle loss, remains powerful, but modern practice increasingly pairs it with normalization techniques, refined losses, richer discriminators, and robust evaluation to meet research standards. Unpaired data unlocks a whole class of image-to-image translation problems, but the practical takeaway goes beyond the basic idea. When you design CycleGAN-style systems for real projects, you're balancing data flexibility with stability, fidelity, and evaluability. Here are some advanced levers that researchers and practitioners actively tune. First, training stability and realism. Even with unpaired data, the discriminator's capacity can drive unstable dynamics if not controlled. Spectral normalization is a widely adopted technique to constrain the discriminator's Lipschitz constant, helping preserve training signals as you scale to higher resolutions or more complex domains. Gradient penalties, inspired by WGNGP, provide an alternative regularization that encourages smooth, meaningful gradients and reduces mode collapse. In practice, many pipelines also use a patch-GAN discriminator to emphasize local textures and high-frequency details, which often matter most for perceptual realism in domains like landscapes, medical textures, or artistic rendering. Second, beyond cycle consistency. The basic ABA loop is essential, but it can be too permissive. Researchers augment the objective with identity losses to discourage unnecessary color or semantic changes when the input already belongs to the target domain. More recently, contrastive or perceptual losses seen in contrastive unpaired translation (CUT) and related approaches encourage the model to preserve content structure while allowing domain-specific style. These ideas can produce sharper, more faithful translations without sacrificing the unpaired data advantage. Third, evaluation and metrics. Quantifying success in unpaired translation is non-trivial. Freshet inception distance, 6 millid, and kernel inception distance, 6 millid, measure distributional similarity between generated and real images, but they can miss fine-grained artifacts. LPIPS offers a perceptual similarity measure for content preservation. A robust evaluation plan combines quantitative metrics with task-relevant criteria and human judgments, and should include checks for semantic consistency and potential artifacts in critical regions. Fourth, hybrid and multi-domain models. In practice, you may have both unpaired data and some paired examples, or you may want translations across more than 2 domains. Hybrid or semi-supervised frameworks leverage available paired samples to anchor the translation, while unpaired data provides breadth. Models like multi-domain translators and contrastive divided by identity augmented variants illustrate how hybrid strategies can improve reliability and control without abandoning the data freedom of unpaired training. Fifth, data and deployment considerations. Domain coverage, power law data distributions, and domain shift matter more than raw quantity. Pre-processing, normalization, and careful data curation reduce spurious correlations. Finally, artifacts and misalignments can pose risks in applied settings (G), medical imaging, or safety-critical graphics. So, rigorous validation and domain-specific evaluation are essential. In short, unpaired training expands what we can translate across domains, but success hinges on stability safeguards, richer loss formulations, robust metrics, and thoughtful data practices. CycleGAN presents a robust framework for unpaired image-to-image translation by maintaining 2 generators and 2 discriminators, enabling bidirectional mapping between domains. Beyond the intuitive idea of translating in both directions, the real strength lies in how cycle consistency acts as a powerful regularizer. The image you obtain after translating A to B and then back to A should resemble the original A. This constraint keeps content and structure stable while still allowing stylistic change, which is crucial when we lack paired examples. From an optimization perspective, several advances have sharpened cycle GAN's performance and reliability. One line of work focuses on training stability. Spectral normalization applied to discriminators controls the Lipschitz constant and stabilizes gradient flow, reducing the risk of discriminator overpowering the generators. Another approach brings gradient penalties, as in WGN-GP, to enforce smooth, well-behaved updates and prevent pathological loss landscapes. Together, these techniques help the model converge more predictably, especially on high-resolution images or datasets with substantial domain gaps. Moving beyond stabilization, evaluation has matured. While cycle consistency guarantees content preservation, we need quantitative measures of realism and alignment across domains. Frechet inception distance is now commonly used to compare the distribution of generated images with real samples in the target domain, offering a sense of global quality and diversity. Perceptual metrics such as LPIPS quantify how perceptually close the translations are to reference images, and kernel inception distance provides complementary statistics. Human judgment and task-specific metrics like structural similarity or domain-appropriate criteria remain important for nuanced assessments. Architecturally, several enhancements pair naturally with CycleGAN's dual-path design. Attention mechanisms can focus the translation on semantically relevant regions, improving realism where it matters most. Patch-based discriminators, patch GAN, encourage finer texture consistency, which matters for materials, foliage, and other detailed textures. Hybrid models fuse cycle GAN with complementary paradigms, integrating perceptual losses from pre-trained networks, coupling with variational or diffusion-based priors for sharper outputs, or combining with segmentation priors to enforce semantic fidelity. There are also practical variants that incorporate identity mapping losses to better preserve color when source and target domains share content but differ in style. In practice, CycleGAN remains versatile for color divided by style transfer, restoration, and cross-domain synthesis, even with non-parallel data. When deploying it, consider additional losses for content preservation, monitor with robust metrics like FID and LPAPS, and experiment with normalization and penalty schemes to stabilize training. Together, these advances extend CycleGAN from a clever trick to a dependable component of modern cross-domain image synthesis. Expanding on the CycleGAN idea, there is a rich set of practices and metrics that researchers increasingly rely on to push beyond simply look real to look real and stay faithful. Let's go deeper into stability, evaluation, and design choices that matter in real-world experiments. First, stability and convergence. Traditional adversarial training can be unstable, especially when you couple two generators and two discriminators. A common stabilization route is to enforce Lipschitz continuity on the discriminators. Spectral normalization is a lightweight, effective technique that constrains the spectral norm of each layer, helping the discriminator provide more meaningful gradients. Another approach is gradient penalties, as in WGN-GP, which penalizes deviations from the one Lipschitz condition. When adapted to cycle GAN style architectures, these penalties can reduce mode variance blowups and improve the reliability of the cycle constraints during training. In practice, you may see a combination, a discriminative backbone stabilized with spectral normalization, plus a small gradient penalty term to keep updates smooth without sacrificing expressiveness. Second, evaluation metrics and what they tell you. The Frechet inception distance has become a standard for assessing both realism and diversity, but it is not the sole measure. LPIPS perceptual similarity can quantify how close the translated outputs are to reference styles in feature space, offering a complementary view to FID. Precision divided by recall-like metrics for generative distributions help diagnose mode coverage, whether the model truly explores the target domain or collapses to a few modes. It's also prudent to combine quantitative metrics with human judgments for nuanced judgments about style and content fidelity, especially in high-stakes domains like medical imaging or satellite data. Third, richer loss, design, and architecture. Identity loss can encourage color and texture preservation when mapping across domains with different appearances but shared content. Perceptual or feature matching losses using features from a pre-trained network can encourage smoother, more semantically consistent translations beyond pixel-wise constraints. On the architectural side, patch GAN discriminators capture high-frequency textures, and multi-scale discriminators provide feedback at different granularities, improving both local realism and global coherence. Architectural choices often go hand in hand with loss weighting. You may adjust cycle, identity, and adversarial weights during training to prioritize content preservation or realism as needed. Finally, hybrid models and latent representations. Hybrid frameworks that blend cycle GAN with variational autoencoders or disentangle latent representations can separate content and style more explicitly. Techniques from DRIT or Munich-style models leverage content encoders or multiple domains to achieve more controllable translations. In practice, researchers experiment with these hybrids to balance faithful content retention with flexible style manipulation while maintaining cycle consistency as a grounding constraint. The takeaway: advance beyond a single loss by stabilizing training, adopting robust evaluation, enriching loss terms, and exploring hybrid architectures to achieve translations that are both believable and faithful. Building on the unpaired translation capabilities of CycleGAN, we can push the discussion toward stability, evaluation, and practical hybrids that researchers care about in real projects. One lever for stability is spectral normalization in the discriminator. By normalizing the spectral norm of each weight matrix, you constrain the discriminator's capacity to produce extreme gradients, helping the generator learn more gradually and preventing training from oscillating. This is especially valuable in cycle-based setups where two generators and two discriminators can amplify instability. Relatedly, gradient penalties, most famously the WGN-GP approach, impose a soft Lipschitz constraint via a penalty on the gradient norm with respect to interpolated samples. In practice, WGANG P-style penalties often yield more stable convergence, reduce mode collapse, and improve the quality of translations in both directions of the cycle. Moving to evaluation, we rely less on subjective judgments and more on quantitative metrics that reflect perceptual realism and consistency. The Fréchet inception distance, or FID, compares the distributions of real and generated images in a feature space from a pre-trained network, capturing both fidelity and diversity. Lower FID is better, but it should be interpreted alongside complementary measures such as inception score IS, kernel inception distance, KIDR, and perceptual similarity metrics like LPIPS. It's also prudent to pair automatic metrics with human judgments for artifacts that fool metrics but remain detectable to observers. When adopting multi-domain or hybrid models, these metrics can be computed domain-wise to diagnose where a model excels or falters. Hybrid models offer a middle path that leverages strengths from multiple paradigms. In cycle-GAN-like architectures, adding an identity loss can encourage color and texture preservation when the input and target domains share content. Perceptual losses, drawn from deeper feature maps, help maintain semantic content during translation. Hybrid approaches also blend supervised and unsupervised signals when partial pairing exists. You can train a cycle GAN with a subset of paired examples to anchor the translation while using unpaired data to broaden coverage. Multi-domain frameworks, A.g. StarGAN style architectures extend the idea to more than two domains, enabling a single model to handle style, lighting, or modality shifts. Hybrid GANs can also fuse with other generative paradigms, such as VAEs for a probabilistic latent space or diffusion-inspired refinements that improve realism while retaining cycle consistency. In practice, the methodological choice hinges on data availability, desired control over style versus content, and the evaluation regime you commit to. If paired data are reliable, traditional supervised GANs with strong regularization can be most efficient. If pairs are scarce or costly, cycle GAN with optional identity or perceptual terms, augmented by spectral normalization and gradient penalties, plus robust FID-based evaluation, tends to yield the most reliable results. Tonight's slide pulls back the curtain on cycle GAN, a kind of image translator that works without paired examples. The Monet to photo example shows how a painting can become a believable photograph of the same scene while keeping the people, objects, and layout intact. It learns two directions, painting to photo and photo to painting. So, content and style are separated. Content remains recognizable, style shifts to the look of a real image. That idea unlocks many applications beyond simple style transfer. We'll see how it can sharpen old photos, turn rough sketches into realistic images, and even adapt visuals to different domains, like vintage looks or surreal worlds. In wildlife studies and medicine, the same principle helps create more data and clearer comparisons without extra scans or labels. We'll also consider reliability, ethics, and practical demonstrations like a horse and zebra sketch before moving to the implications for care and research. The Monet to photo example is not just a pretty illustration of cycle GAN's capabilities. It's a concrete demonstration of content style disentanglement, learned without paired data. In practice, two domains, the painting domain and the photo domain, are connected by two generators, painting to photo and photo to painting. Each direction has its own discriminator, and training optimizes adversarial objectives while enforcing cycle consistency. The key idea is that the network learns what parts of the image convey the scene's content, objects, layout, people, and what parts convey its style, brushwork, color palette, texture. The result is the same scene rendered in two different appearances without requiring exact pixel for pixel pairs. Beyond this basic picture, several advanced design choices stabilize and improve the translation. First, many implementations adopt patch GAN discriminators, which operate on local image patches A, G, 70 times 70. This encourages high quality texture and detail without forcing a globally perfect alignment, letting the model capture realistic microstructures such as reflections, foliage, or brush textures. Second, cycle consistency losses ensure that translating there and back preserves core content, while identity losses help preserve color and tonality when inputs already resemble the target domain. From a training stability perspective, researchers have introduced improvements such as spectral normalization in discriminators to bound the Lipschitz constant and mitigate exploding gradients. Gradient penalties, inspired by WGAN-GP, offer an alternative regularization that enforces smoother discriminator landscapes. These refinements help cycle GAN converge more reliably and produce outputs with crisper details and fewer artifacts. Evaluating these models calls for more than visual inspection. Quantitative metrics such as freshet inception distance (FID) assess how close the distribution of generated photos is to real photos in a learned feature space. Kernel inception distance key offers a complementary unbiased measure. Perceptual similarity metrics like LPIPS and structural metrics like SSIM provide insight into how well content is preserved and how convincing the style transfer feels. Human studies remain valuable for judging artistic faithfulness and perceptual quality, especially in nuanced style cases. Hybrid approaches are active areas of research. You can combine cycle GAN with attention mechanisms to focus stylization on informative regions, or incorporate segmentation maps to preserve structural boundaries. Perceptual or feature modality losses from pre-trained networks can guide style adaptation more faithfully. Some researchers even couple cycle GAN with diffusion-based refinements as a post-process to sharpen textures while maintaining content fidelity. Cycle GAN gave us a pragmatic way to translate images without paired examples, but in wildlife research, the stakes for realism and reliability are higher. Today, I'll push beyond the basic cycle consistency picture and outline how researchers actually stabilize, evaluate, and hybridize these models to make them trustworthy tools in the field. First, consider training stability and the quality of fine-scale details. A key upgrade is spectral normalization on the discriminator. By constraining the Lipschitz constant of the critic, we dampen excessive gradients that can destabilize unpaired translation and reduce artifacts that creep into fine textures like fur patterns or feathering. In tandem, a gradient penalty term inspired by WGA and GP encourages a smoother discriminator surface, which helps the generator learn more robust, gradual mappings rather than chasing sharp, brittle distinctions. These two together tend to improve convergence and produce more consistent outputs across diverse lighting and backgrounds. Second, move beyond pixel-level losses to perceptual guidance. Identity loss can be added so that when you feed an image from domain A to the AB generator and it's already in the target style, the output remains close to the input. Perceptual or feature-based losses computed from a pre-trained network like VGG help preserve higher-level structure and texture, strengthening background realism and animal geometry while still allowing the domain transfer. In practice, this reduces drift in pose and scene layout that sometimes accompanies unpaired translations. Third, adopt richer evaluation and diagnostic metrics. The Frechet inception distance, or FID, is a standard for quantifying realism by comparing distributions of real and generated images in a feature space. It's particularly informative when you want to track progress across training iterations. LPIPS, a perceptual similarity metric, can help assess whether the translated image preserves essential content from the source. Human expert review remains indispensable, but these quantitative metrics give us objective signals for hyperparameter tuning and model comparison. Fourth, explore hybrid architectures that keep cycle GAN honest about content while leveraging structure-aware priors. Attention mechanisms or segmentation masks can guide the model to focus on the animal region, leaving the background to be transformed more conservatively. Masked cycle losses or region-specific discriminators improve background preservation and reduce background swapping. Multi-scale discriminators, evaluating both global layout and local textures, capture coherence at different spatial levels. Finally, in wildlife studies, remember the three practical aims. 1. Improve species recognition in camera trap data. 2. Support behavioral and movement analysis with consistent imagery. And 3. Provide data augmentation that enhances model robustness. With ethical labeling and careful validation, recognizing synthetic images in publications and preventing misuse, we can harness these advances to study nature more deeply without compromising integrity. Let me take you a bit deeper into how cross-modality translation, exemplified by CycleGAN, can be made more reliable and clinically meaningful. We are not just translating pixels, we are stabilizing learning, validating results, and aligning with clinical needs. First, on training stability and realism. Traditional GAN losses can be fragile when working with medical images where subtle texture and fine detail matter. To address this, two techniques are frequently employed. Spectral normalization constrains the discriminator's spectral norm, helping to stabilize training and prevent the discriminator from becoming too strong. Gradient penalties, such as those used in WGAN GP, enforce Lipschitz continuity, reducing oscillations and improving convergence. Together, they give us more faithful mappings between MRI and CT domains, and fewer artifacts that could mislead a clinician. Second, architectural and objective refinements. The cycle consistency loss remains essential, but we often augment it with an identity loss to encourage the network not to change content that already lies in the target domain. Patch-based discriminators, often called PatchGAN, focus on local texture and structure, which is critical for preserving clinically important details like subtle calcifications or trabecular patterns. Attention modules and residual connections help the model emphasize regions that bear diagnostic relevance, such as lesions or organ boundaries. For volumetric data, 3D CycleGAN variants or hybrid 2D 3D approaches capture interslice consistency at the cost of higher memory requirements. Multiscale discriminators give us both global coherence and local fidelity, which matters when translating coarse anatomical layouts alongside fine-grained tissue textures. Third, evaluation strategies that go beyond visual realism. In academia and practice, fresh at inception distance (FID) provides a global distributional similarity measure, but medical imaging benefits from task and view-specific metrics. Pairing FID with SSIM, PSNR, and mutual information can quantify structural and statistical fidelity. More clinically, radiologists scoring lesion level detection or segmentation accuracy and task-driven metrics A. G. How translation affects diagnostic confidence or segmentation performance are crucial. When paired data are scarce, phantom studies and synthetic benchmarks can help, and calibration studies can quantify the risk of hallucinated features. Fourth, safety, fairness, and deployment considerations. Cross-modality translation can inadvertently introduce artifacts or erase subtle findings. Pharmacokinetic or physics-based priors incorporating known MRI divided by CT acquisition physics, noise models, or attenuation properties can constrain translations to lie within plausible ranges. Federated or privacy-preserving training can widen data access across institutions without exposing patient data, improving generalization. Before we dive in, we'll connect the dots between what CycleGAN can do today and what it struggles with in practice. We've seen that color and texture can drift when translating between domains, and fine details in busy scenes often blur or misplace. These gaps aren't just quirks, they reveal where the mapping learns the broad shape of a scene but misses local cues like hairs, fabrics, or edge textures. To push beyond that, researchers add perceptual and identity losses and bring attention to guide changes only where it matters. We'll explore how these ideas reduce artifacts and keep layout and mood more faithful, especially in complex images. We'll also peek at multi-domain translation, scaling up to many styles without paired data, plus the dream of real-time performance on everyday devices with pruning, quantization, and lean architectures. Today, we look at the current limitations of CycleGAN in image translation. Beyond the intuition of color mismatches and stray textures, a more critical view reveals how the training dynamics and architectural choices gate the quality of the translation. From a technical perspective, the discriminator can overfit to global color cues while ignoring fine textures, leading to inconsistent transfers across regions. One remedy is to stabilize the adversarial training with spectral normalization, which constrains the Lipschitz constant of the networks and dampens pathological gradient growth that tends to exaggerate color shifts. Another is gradient penalties, as in WGAN GP, to enforce smoother discriminators and align gradient signals across neighborhoods, reducing artifacts that look like color halos or smeared textures. Handling complex scenes with many details remains challenging. High-frequency textures such as hair, fabric weaves, or signage boundaries require careful cross-domain alignment. Multi-scale discriminators, coupled with patch-based evaluators, help the model attend to both global layout and local structures. Attentional modules and self-attention allow the generator to preserve relationships between distant regions, so objects retain coherence when crowded. Perceptual losses. Computing feature space distances in a pre-trained network encourage the model to preserve textures and overall look beyond pixel-level similarity. In practice, researchers also employ coarse-to-fine or multi-stage pipelines, a rough translation followed by a refinement pass that corrects misaligned details. Preserving layout and geometry is still fragile when scenes contain many objects. We can inject alignment cues, geometry-aware losses, or spatial transformer components that encourage the mapping to respect scene, structure, and object placement. This is complemented by identity losses to preserve shading and lighting cues across domains, and by semantic priors learned through auxiliary networks. On evaluation, the field now uses freshet inception distance (FID) and kernel inception distance to quantify distributional similarity, plus LPIPS for perceptual distance and human studies for realism. None of these are perfect alone. Robust evaluation blends automatic metrics with human judgments and ablation studies. Finally, there is growing interest in hybrid models, combining cycle consistency with diffusion refinements or integrating contrastive and clip-based losses to align semantic content, which can dramatically improve semantic preservation while maintaining style change. Let me present how enhanced cycle-consistent methods push beyond the baseline by integrating perceptual and identity cues with attention, and how this combination improves both fidelity and style transfer in challenging settings. At the core, perceptual loss uses features from a pre-trained network to measure high-level similarity between a translated image and its target. Identity loss further constrains the mapping to preserve content when the input already belongs to the target domain. When you fuse these with cycle consistency, the model learns not only how to translate style, but also what should remain invariant texture, geometry, and fine structures survive the change of domain. The practical payoff is translations that keep global meaning intact while preserving textures and edges, reducing blur and implausible artifacts that plague simpler cycles. Attention mechanisms add another lever. They tell the model where to apply changes. By injecting self-attention or non-local blocks into generators and sometimes into discriminators, the network can capture long-range dependencies and complex interdependencies across a scene. This is crucial for detailed mappings and long-range patterns, think cityscapes, forests, or textured materials where local patches alone cannot convey coherence. When you couple attention with cycle loss and perceptual constraints, the model learns not just what to change, but where to change it, yielding sharper textures, more accurate edges, and more faithful style transfer in complex layouts. There is a family of variants worth noting. Self-attention modules can be placed at multiple scales to model both global context and local detail. Some approaches mix local attention with global context to balance efficiency and coherence. Multi-scale discriminators paired with attention help the model evaluate realism at different resolutions, which further stabilizes training and improves texture fidelity. In practice, attention-guided cycle losses concentrate the model's capacity on perceptually important regions, such as eyes, wheels, or architectural edges, while leaving less critical areas relatively untouched. Beyond architectural choices, researchers deploy stabilization tricks that matter in practice. Spectral normalization stabilizes the discriminator's learning dynamics, and gradient penalties, as in WGAN GP, encourage smoother, more reliable updates. These techniques complement perceptual and identity losses by supporting consistent optimization in high-capacity, attention-rich networks. Evaluation now routinely uses metrics like FID or KID for realism, LPIPS for perceptual similarity, and SSIM divided by PSNR for structural fidelity, often in conjunction with human judgments. For researchers, a practical workflow is start with a perceptual plus identity plus cycle objective, add a light attention module, and monitor stability with spectral normalization and gradient penalties. Use a few ablations to quantify the contribution of attention and perceptual terms and track FID divided by LPAPS trends across iterations. In short, the synergy of perceptual and identity losses with attention addresses the core weaknesses of standard cycle consistent models in complex scenes, delivering translations that are both visually convincing and semantically faithful. We'll illustrate these gains with concrete examples next. Building on cycle GAN, today I want to discuss how we move toward scalable, multi-domain translation and real-time deployment, while keeping fidelity and content integrity intact. The key question is not just can we translate between many styles, but can a single model manage dozens of domains without exploding in size or training time and still deliver results fast enough for practical use? Imoringu. First, multi-domain translation introduces stability and efficiency challenges. As the number of domains grows, naive one-to-one pairs or separate models become impractical. A productive direction is to design scalable architectures that share knowledge across domains. Think of a shared encoder that captures a rich, domain-agnostic representation and a set of domain condition decoders or adaptive normalization layers, for example ADDING or FLM, that steer the output toward a given style. Self-attention or cross-domain attention modules help the model align content while changing style, preserving structure and geometry across domains. In practice, you also want to enforce strong cycle consistency across multiple domains and complement it with identity losses and feature-level cycle constraints to reduce drift at the perceptual level. From a training perspective, stabilization and generalization across many domains benefit from modern regularizers. Spectral normalization on discriminators combined with gradient penalties as in WGAN GP helps maintain Lipschitz continuity and prevents exploding gradients when domains vary widely. You can also incorporate perceptual or content-preserving losses derived from pre-trained network features to encourage faithful content transfer. Hybrid approaches blending GANs with diffusion steps or variational components are increasingly explored to improve sharpness and mode coverage while retaining conditioning control. For researchers, such hybrids offer a path to sharper translations without sacrificing the flexibility of multi-domain conditioning. Evaluation becomes more nuanced in this setting. Beyond qualitative inspection, we rely on metrics like freshet inception distance and its foster cousin KID to quantify distributional similarity between generated and real images per domain. Perceptual similarity measures such as LPIPS help assess content preservation at a feature level. Domain-specific evaluations such as style accuracy, color distribution matching, and sometimes human judgments remain important, especially for high-stakes applications. For video or real-time streams, temporal consistency metrics and subjective latency assessments complete the picture. On the deployment side, real-time capability demands efficiency. Pruning and structured sparsity reduce compute without heavily compromising quality. Quantization, distillation, and careful backbone design. Lightweight encoders, compact decoders, push models toward mobile and edge devices. Architecture search and hardware-aware optimizations further close the gap to deployment-ready performance. Today's finish brings the discussion to a clear close. As we move from the framing of the central question through the methods and evidence presented, the deck culminates in a concise synthesis of conclusions. The summary emphasizes the core insights, their significance for the field, and the practical implications for policy, practice, or further study. At the same time, it acknowledges limitations and the boundaries within which these findings hold, inviting cautious interpretation and constructive critique. The wrap-up also points to questions that remain open and to avenues for future inquiry, encouraging readers to build on what has been established rather than to view it as final. Thank you for your engagement with this material and for the opportunity to reflect on its broader relevance. Building on CycleGAN's core idea, there is a rich set of refinements that researchers are actively exploring to improve stability, fidelity, and evaluability in unpaired image-to-image translation. First, stability and learning dynamics have benefited from regularizing the discriminators. Spectral normalization constrains the Lipschitz constant of each discriminator, which helps prevent sudden, unstable updates and keeps the learning signal well behaved across training. Gradient penalties, as popularized by WGAN GP, enforce a soft constraint on the gradient norm of the discriminator when samples are taken along interpolations between real and generated images. In practice, these techniques reduce mode collapse and often allow for larger, more stable training steps. Some implementations also favor hinge losses in the adversarial objective, which can further stabilize optimization and yield crisper textures. Second, architectural choices sharpen how information is preserved and styled. Patch-GAN discriminators assess realism at the level of local patches, encouraging fine-grained texture consistency, while multi-scale discriminators enforce realism across different spatial resolutions. Generators frequently adopt UNet-style architectures with skip connections to preserve spatial content and increasingly incorporate attention mechanisms to localize style transfer to semantically relevant regions. An auxiliary identity loss can be added to encourage the generator to leave inputs that already belong to the target domain largely unchanged, helping to preserve color and simple structures when appropriate. Third, how we evaluate these models matters as much as how they are trained. Fréchet inception distance and its kin-Kate quantify distributional similarity between translated images and real images in the target domain, but they must be interpreted cautiously in unpaired settings. Perceptual metrics such as LPIPS measure structural similarity in feature space, while SSSIM-like indices can quantify content preservation. Complementary human judgments or task-specific evaluations. A. G. Downstream segmentation or diagnostic accuracy in medical imaging are often essential to complement these metrics. Fourth, there are practical strategies and hybridizations to push cycle GAN further. Replay buffers stabilize discriminators by reusing past-generated images. Semi-supervised variants can leverage a small pad subset to seed more accurate mappings. Hybrid models combine cycle GAN with variational or perceptual constraints or with semantic or content-aware losses to improve disentanglement of content and style. For video and 3D data, temporal or spatial consistency losses extend the cycle idea across time or across slices, reducing flicker and preserving coherent structure. In short, two translators and two critics remain the core, but spectral normalization, gradient penalties, richer discriminators, advanced evaluation, and hybrid training strategies collectively broaden cycle GAN's reach while enhancing reliability and interpretability. This cycle GAN notebook explores how machines can translate images between domains without needing paired training data. Traditional methods require exact image pairs, like the same street in both sun and rain. Cycle GAN changes that by introducing cycle consistency. If an image is transformed from one domain to another, it can also be translated back in a meaningful way. With this idea, cycle GAN unlocks creative possibilities such as turning horses into zebras, photos into paintings, or summer into winter scenes, all without strict data requirements. More than just an algorithm, cycle GAN highlights how AI can act as a creative partner. It learns the subtle features of style, texture, and context, enabling new tools for artists, designers, filmmakers, and researchers. This notebook is both technical and imaginative. It shows how models master complex translations while raising questions about creativity, ethics, and application. Cycle GAN stands as a milestone in deep learning, pushing image synthesis from recognition toward creation. In this section, we begin by importing the essential libraries needed for our project. We load the TensorFlow datasets module, which provides easy access to a variety of datasets, and specifically import the Pix2Pix model components from TensorFlow's examples, which we'll use for image-to-image translation tasks. Next, we bring in the OS and time modules to handle operating system interactions and timing functionalities, which are useful for managing file paths and measuring performance. For visualization purposes, we import matplotlib, pyplot, a standard library for plotting images and graphs, and also include clear output from IPython. Display to help manage the notebook's output display, especially when visualizing results dynamically. Finally, we set a constant auto-tune from TensorFlow's data API, which allows TensorFlow to optimize data loading and pre-processing by automatically tuning performance parameters. This setup ensures our environment is ready with all necessary tools for building, training, and visualizing our cycle GAN model effectively. In this section, we start by loading the dataset using TensorFlow datasets. Specifically, we load the cycle GAN divided by horse to zebra dataset, which contains images of horses and zebras. By setting the parameter with info equals true, we also retrieve some metadata about the dataset, and with as supervised equals true, the data is loaded in a simple supervised format, pairing input images with their labels. Once loaded, the dataset is a dictionary containing separate splits for training and testing, each further divided into two parts, one for horses and one for zebras. We assign these splits to variables for clarity, naming the training images of horses as train horses and the training images of zebras as train zebras. Similarly, we do the same for the test images, storing them in test horses and test zebras. This setup prepares the data for subsequent processing and training of the cycle GAN model, ensuring that each domain's images are clearly separated and accessible for the next steps. In this section of the notebook, we define some fundamental parameters used throughout the model training process. The first parameter, buffer CZ, is set to 1000, which determines the size of the buffer used for shuffling the data set. This helps ensure that the data is mixed thoroughly, promoting better training outcomes. Next, the batch size is set to 1, indicating that the model will process one image at a time during each training step, which is typical for certain types of generative adversarial networks like cycle GAN, especially when working with high-resolution images. We also specify the dimensions of the input images with IMG, VDEH, and IMG height both set to 256. This standard size ensures consistency in the data and simplifies the neural network architecture, as it expects inputs of this fixed size. Overall, these parameters are crucial for controlling how the data is fed into the model and directly influence the training process and the quality of the generated images. We define a function called random crop that takes an image as its input. Inside this function, we utilize tensorflows.tf image random crop method, which randomly extracts a crop from the input image. The size of this crop is specified to match the desired height and width, represented by IMG height and IMG width along with 3 color channels. This operation helps in augmenting the dataset by creating varied crops from the original images, which can improve the robustness of the model during training. After cropping, the function returns the resulting image, now a randomly selected section of the original. This code defines a function called normalize that is used to pre-process images for the neural network. The primary purpose of this function is to scale the pixel values of an image so that they fall within the range of -1 to 1. First, it converts the input image to a floating point data type, ensuring that subsequent mathematical operations are performed accurately. Then, it divides each pixel value by 127, 5, which effectively scales the original pixel values, typically in the range of 0 to 255, down to a range approximately between 0 and 2. After this division, it subtracts 1 from each pixel value, shifting the entire range so that the pixel values now span from -1 to 1. This normalization step is important because many deep learning models perform better when the input data is scaled to a consistent range, particularly symmetric ranges like -1 to 1. By doing so, the model can learn more efficiently, leading to better convergence during training. This function, called notRandomJitter, is designed to introduce some variability into the images during training, which helps improve the robustness of the model. First, it takes an input image and resizes it to 286 by 286 pixels using nearest neighbor interpolation. This slightly larger size allows for random cropping later on. Next, it applies a random crop to bring the image back down to 256 by 256 pixels, which is a common size for training in deep learning models. The cropping is performed by a separate function called .randomCrop. After cropping, the function randomly flips the image horizontally, which helps the model learn invariant features regardless of the image's orientation. Finally, it returns the augmented image, ready for training. This combination of resizing, cropping, and flipping introduces randomness that helps the model generalize better to different variations of the input data. This code defines a function called preprocess image train, which is used to prepare images during the training phase of a cycle GAN model. The function takes two inputs, an image and its corresponding label, although in this particular implementation, the label isn't used within the function itself. Within the function, the first step applies a technique called random jitter to the image. This step typically involves random transformations such as cropping, flipping, or scaling, which serve to augment the dataset and improve the model's robustness by introducing variability. Next, the image is passed through a normalize function, which adjusts the pixel values to a standard range, often between -1 and 1 or 0 and 1. Normalization helps the neural network learn more efficiently by ensuring consistent data scales across different images. Finally, the function returns the processed image, now augmented and normalized, ready to be fed into the training process. This combination of jittering and normalization is a common pre-processing pipeline to enhance model performance and generalization. In this section, we define a simple pre-processing function called preprocess image test. This function takes an image and its corresponding label as inputs. Inside the function, the primary operation is to normalize the image, which typically involves adjusting pixel values to a standard range, often between 0 and 1, to facilitate better model performance during testing. After normalization, the function returns the processed image, effectively preparing it for evaluation or inference in the testing phase of the cycle GAN model. Notably, the label is not used within this function, indicating that during testing, only the image itself is relevant for preprocessing. This section of the code focuses on preparing the datasets for training and testing. First, it processes the horse training images by applying a pre-processing function designed for training data, which likely includes data augmentation techniques. The images are cached to improve performance during repeated epochs, then shuffled to ensure the model doesn't learn any order-based biases. After shuffling, the data is batched into smaller groups according to the predefined batch size for efficient training. Similarly, the zebra training images undergo the same sequence. They are pre-processed with the training-specific function, cached for faster access, shuffled to promote randomization, and batched appropriately. For the test datasets, the process is slightly different. The images are mapped through a separate pre-processing function tailored for testing, which might exclude augmentation to evaluate the model on unaltered data. These are also cached, shuffled, and batched, ensuring that the evaluation data is prepared consistently with the training data, but without the augmentations used during training. This systematic preparation facilitates efficient and effective training and evaluation of the cycle GAN model. Here, we are retrieving sample images from the training datasets for both horses and zebras. By calling nextIder_train horses, we obtain the first batch of horse images, and similarly, nextItTrain zebras fetches the first batch of zebra images. These samples are typically used later in the notebook for visualization or comparison purposes, allowing us to see how the images look before any transformations or training steps have been applied. This code segment is dedicated to visualizing images using matplotlib. First, it creates a subplot with two side-by-side images. The left subplot displays the original horse image, which is retrieved from the sample data. Since the image data might be normalized between -1 and 1, multiplying by 0, 5, and adding 0. 5 rescales it to the standard 0-1 range suitable for display. The title horse clearly indicates this is the original image. Moving to the right, the second subplot shows the same horse image but with a layer of random jitter applied. This jitter introduces small random variations or distortions which can help in data augmentation or in visualizing how the model might handle slight perturbations. Again, the image is rescaled for proper visualization and is titled horse with random jitter. This side-by-side comparison allows us to observe the effect of the jitter directly, providing insight into how data augmentation techniques might influence the training process or the model's robustness. In this section, we focus on visualizing the results to better understand how the model performs. The first subplot displays an original zebra image, which is obtained from our sample dataset. To ensure proper display, we adjust the pixel values from the range of -1 to 1 back to the standard 0 to 1 scale by multiplying by 0, 5, and then adding 0. This normalization step helps the image appear correctly in the visualization. Next, in the second subplot, we present the same zebra image but with a random jitter applied. This jitter introduces slight variations or distortions, simulating different conditions or augmentations that the model might encounter. Again, we normalize the pixel values for proper display. By placing these images side by side, we can easily compare the original image with its jittered version, providing insights into how data augmentation affects the input and helping us assess the robustness of the model. In this section of the notebook, we start by defining the number of output channels, which is set to 3, corresponding to the color channels in an RGB image. Next, we initialize two generator models using a unit architecture, one designated as generator G and the other as generator F. Both generators are configured to produce 3-channel images and utilize instance normalization to stabilize training and improve image quality. Following that, we set up two discriminator models, discriminator X and discriminator Y, each employing instance normalization as well. These discriminators are designed to evaluate the authenticity of images in their respective domains, with the target parameter set to false, indicating that they are standard discriminators without additional target conditioning. Overall, this setup prepares the core components needed for a cycle GAN model, enabling the translation between two different image domains. In this section, we are visualizing the results of our cycle GAN model. First, we generate a zebra image from a sample horse image using the generator designated for horse to zebra translation. Similarly, we convert a sample zebra image back into a horse using the zebra to horse generator. Next, we set up a figure with a size of 8 by 8 inches to display our images clearly. We define a contrast variable to enhance the visualization of the generated images. We prepare a list of images including the original horse and zebra images as well as the generated ones and assign appropriate titles for each. We then iterate over these images, creating a 2 by 2 grid of subplots. For each image, we assign the corresponding title. When displaying the original images, we simply rescale the pixel values from the range -11 to 01 for proper visualization. For the generated images, we additionally multiply by the contrast factor to enhance their features before rescaling. Finally, we call PLT to display the composite figure, allowing us to visually compare the original and translated images side by side. This provides a clear and intuitive way to assess how well the model is performing in translating between horses and zebras. Here, we start by creating a new figure with a size of 8 by 8 inches to provide enough space for our visualizations. We then set up two subplots side by side. In the first subplot, we assign the title is a real zebra and display an image that results from passing a sample zebra image through the discriminator designed to identify zebras. We extract the relevant output channel, which indicates the discriminator's confidence, and visualize it using a red-blue color map to highlight the areas of certainty or doubt. In the second subplot, we title it is a real horse and display the output from the horse discriminator when it evaluates a sample horse image. Again, we extract the corresponding output channel and visualize it with the same color map, allowing us to compare how each discriminator perceives the authenticity of the images. Finally, we call PLT to render these visualizations, providing a clear side-by-side view of the discriminator responses for a zebra and a horse. We define a loss object using TensorFlow's built-in binary cross-entropy loss function. By setting the parameter from logits equals true, we specify that the predictions coming from the model are raw logits, meaning they are not passed through a sigmoid activation function. This configuration allows the loss function to internally apply the sigmoid, which improves numerical stability and ensures accurate computation of the loss during training. This loss object will be used later to evaluate how well the discriminator or generator models are performing by comparing their predicted outputs with the true labels. This function, named discriminator loss, calculates the loss for the discriminator in a cycle GAN model. It takes two arguments, real, which represents the discriminator's output for real images, and generated, which represents its output for generated images. Within the function, we first compute the loss for real images by comparing the discriminator's output to an array of ones, since we want the discriminator to classify real images correctly as real. This is done using a loss object, loss obj, which is typically a binary cross-entropy loss. Similarly, we calculate the loss for generated images by comparing the discriminator's output to an array of zeros, since we want the discriminator to correctly identify generated images as fake. Next, we sum these two losses to get the total discriminator loss. To keep the loss scaled appropriately, we multiply this total by 0. Woo. This averaging helps maintain balanced training between the generator and discriminator. The function then returns this final loss value, which guides the training of the discriminator to better distinguish between real and generated images. This code defines a function called generator loss, which takes a tensor called generated as its input. The purpose of this function is to compute the loss for the generator in the cycle GAN model. Inside the function, it uses a loss object .loss obj to compare the generated images against a tensor of ones that has the same shape as the generated images. This essentially measures how well the generator is fooling the discriminator by trying to make the generated images appear as real as possible. The function then returns this calculated loss value. This function, named calc cycle loss, is designed to compute the cycle consistency loss in a cycle GAN model. It takes two inputs, real image, which is an original image from the dataset, and cycled image, which is the image generated after passing through the generator twice, once forward and once backward. The core idea here is to measure how similar these two images are, which helps ensure that the generator can successfully reconstruct the original image after a cycle. To do this, the function calculates the mean absolute difference between the pixel values of the real image and the cycled image using TF. Reduce mean TF of real image phi cycled image. This value quantifies the discrepancy between the two images. Finally, the loss is scaled by a constant factor, lambda, which controls the importance of this cycle consistency term relative to other components of the overall loss function. This scaling ensures that the model maintains a balance between generating realistic images and preserving the content of the original images during the cycle. This function computes the identity loss, which is a crucial component in training cycle GANs to preserve the color composition of images. It takes two inputs, the real image and the image that has been passed through the generator with the same domain. The core of the function calculates the mean absolute difference between these two images, effectively measuring how similar they are. This difference is then scaled by a factor of half and multiplied by a hyperparameter called lambda, which controls the strength of this loss term. Incorporating this loss encourages the generator to produce images that retain the original image's identity, helping maintain consistent colors and styles across transformations. In this section, we set up the optimizers for training the cycle GAN model. We define separate Adam optimizers for each generator and discriminator. Specifically, both generator G and generator F are assigned Adam optimizers with a learning rate of 2e4 and a beta 1 parameter of 0.5, which helps stabilize training by controlling the moving averages of the gradients and their squares. Similarly, each discriminator X and discriminator Y also receives its own Adam optimizer with the same hyperparameters. This setup ensures that each component of the model is optimized independently, allowing for more controlled and stable training dynamics as the generators and discriminators learn to improve their respective tasks. This segment of the code sets up the training checkpoint management for the cycle GAN model. It begins by defining a path where the training checkpoints will be stored, specifically in a folder named checkpoints divided by train. Next, it creates a TensorFlow checkpoint object that tracks all the key components involved in training, the generators and discriminators, along with their respective optimizers. This ensures that the entire training state can be saved and restored seamlessly. A checkpoint manager is then initialized, which manages the saving and loading of these checkpoints, keeping up to 5 recent checkpoints to prevent clutter. The code proceeds to check if there is an existing checkpoint in the specified directory. If a checkpoint is found, it restores the latest one automatically, allowing training to resume from the last saved state. A confirmation message is printed to indicate that the latest checkpoint has been successfully restored. This setup is essential for training continuity, enabling the model to recover from interruptions and ensuring that progress is preserved across sessions. This code defines a function called generate, images that takes a trained model and a test input as its parameters. Inside the function, the model is used to generate a prediction based on the test input. Then, a new figure is created with a size of 12 by 12 inches to display the images clearly. Next, it prepares a list called display, list that contains the original test input image and the predicted image produced by the model. Correspondingly, it sets up a list of titles for these images, input image and predicted image. The function then loops twice to create two subplots side by side. In each loop iteration, it adds a subplot to the figure, assigns a title, and displays the image. To visualize the images properly, it rescales the pixel values from the range 0, 1 to a range suitable for display, which is achieved by multiplying by 0, 5, and then adding 0. Ooh. Finally, it turns off the axis for a cleaner look and displays the complete figure. This way, viewers can easily compare the original input with the model's generated output. This code defines a TensorFlow function called train step, which is decorated with a TF function to optimize its execution. The purpose of this function is to perform one training step of the cycle GAN model, updating the generators and discriminators based on the current batch of real images from two domains, real X and real Y. Within this function, a TF gradient tape is used with persistent equals true, allowing multiple gradient computations within the same context. This is necessary because the code calculates various losses that require gradients from different parts of the network. First, the generator G takes images from domain X and translates them into domain Y, producing fake Y. Then, this fake image is cycled back through generator pre F to reconstruct pre-cycled X. Similarly, generator G phi F translates images from domain Y into domain X, generating fake X, which is then cycled back through generator G to produce cycled Y. The code also computes identity mappings, passing real X through generator F and real Y through generator G, resulting in same X and same Y. These are used for identity loss, encouraging generators to preserve images when the input is already from the target domain. Next, the discriminators evaluate the real images and the generated fake images, disk real X and disk real Y. Assess the authenticity of the real images, while disk fake X and disk fake Y evaluate the fake images generated by the generators. The loss functions are then calculated gen G loss and gen F loss. Measure how well each generator fools the discriminators using a generator loss function. Additionally, the total cycle consistency loss combines the losses from reconstructing the original images from the cycled images, ensuring the generators maintain the content during translation. This setup prepares the ground for computing gradients and updating the models to improve their performance in translating images between the two domains. This code implements the training loop for a cycle GAN model, iterating over a specified number of epochs. At the start of each epoch, it records the current time to measure how long the epoch takes. Inside the epoch, it initializes a counter and then loops through paired datasets of horse and zebra images using TensorFlow's dataset zipper to process them simultaneously. For each pair, it calls a train step function that performs the training update. Every 10 steps, it prints a dot to indicate progress, providing a simple visual cue during training. After processing all image pairs in the epoch, it clears the previous output to keep the display clean, then generates sample images using a fixed horse image to visually monitor the model's progress over time. This helps in assessing how well the generator is translating horses to zebras and vice versa. Every 5 epochs, it saves a checkpoint of the model's current state, ensuring that progress isn't lost and enabling future restoration or analysis. Finally, it prints out the total time taken for the epoch, giving insight into the training duration and efficiency. This structured approach balances training, progress visualization, and model checkpointing seamlessly. This section of the code runs the trained model on the test dataset to generate some example images. It takes the first 5 images from the test set, which consist of horse images, and passes each one through the generator network. The function generate images is called with the generator and the input image, producing a transformed image that can be visualized or saved. This process allows us to see how well the model has learned to convert horse images into the target domain, providing a quick qualitative assessment of its performance on unseen data. This CycleGAN notebook showed how images can be transformed across domains while keeping their core identity intact. Adversarial training drives the generator to create outputs that look real, while the balance of losses and design choices shapes the quality of each result. From horses to zebras, summer to winter, or photos to paintings, we saw how these transformations emerge through careful training and iteration. The key insight is that this is just the start. CycleGAN is a foundation for more advanced systems that could offer finer control, higher fidelity, and even integration with other types of data. These directions point to richer, more immersive possibilities for creative and practical use. As you move forward, I've already shared the code for this notebook in Teams. Please execute it on your end and let me know if you run into any issues. I'll be happy to guide you through.